Okay, guys, so this morning what you're going to be doing is you're going to be testing a simulation on PhET that deals with the electric field created by a dipole. And what we're going to be looking to see is if the simulation gives us the same sort of result that we would get from theory. So what we're going to do now is we're going to figure out what the theoretical expression is. Normally, I let you guys do the lab and kind of play with it before I even show you what the real answer should have been. Um, but I suspect that if I do that for an online version, I won't know when you're done, and I won't be able to prompt you with the appropriate stuff at that time. So let's just think through the theory first, and then we'll see if we get that same behavior. Uh, so let me pull this out. Go to the second camera. Oops, I just clicked right past it because I'm stupid. There we go. All right, so an electric dipole is just two charges of equal but opposite magnitude placed a very small distance apart. Um, when I say a small distance, I mean a really small distance. Uh, a lot of times we talk about the dipole moment of an actual molecule. So if you're looking like a water molecule, the distance that you're talking about is literally the width of a single molecule. That's how close the charges are often placed to one another. And what's going to happen is if these two charges are placed a small distance d apart, if this was one object, the total charge of that object would be zero. And you would expect that an object with zero charge would have zero electric field. But because the charges are separated by a small distance, they don't completely cancel out. And as a consequence, you get a noticeable electric field. And we're about to get the expression for that electric field. Now, in order to do that, we're going to do this in a couple of different locations. And we're going to be testing both those locations today in the lab. One of the locations that we're going to be testing is going to be along the axis of the dipole. So you'll notice these two guys are along the same line. So imagine that's my x-axis, and then let's have my y-axis run straight down the middle. Imagine that I drew that symmetrically. I totally didn't. And what we're going to be doing is looking at the electric field due to those charges at some location. Let's do this location right over here, somewhere on the axis of the dipole. I want to find the electric field there. Now, what's going to happen is there are two electric fields, one from the positive charge and another from the negative charge. The positive charge is going to have an electric field that points to the right because it always points away from positive charges. So I'm going to call that E plus. The negative charge is going to have an electric field that points to the left. So as long as I'm on that axis, the electric field is going to be in opposite directions for those two charges. So they're going to tend to try to cancel out. Now, if I wanted to find an expression for that, what I would do is E plus would be KQ over R squared. And of course, both of their charges are the same number. That's cool. But the R's are going to be different. R is the distance from the charge to where I'm observing. And if this distance right here from the center is X and this distance is D, this is half of D. So the R for the positive charge is going to be all of X plus an extra D over 2. So KQ over X plus D over 2 squared. I got to square that whole thing. So that's the electric field from the positive charge. The electric field from the negative charge, I would get in a similar fashion. KQ over, except wait a second. This guy is actually closer to that point by D over 2. So it's going to be X minus D over 2. because it's a little bit closer. Now, conveniently for us, since the electric fields are in opposite directions, all I've got to do is add these two things together. But since this one is to the left, I'm going to make it negative. So my total electric field is going to be KQ over, all right, that's the positive part, minus the negative part. So that's what the electric field should look like. And this is kind of an ugly, complicated looking expression. And so what we often do is we try to make that expression a little bit less ugly. And one way I could do that is by combining these into like one big fraction. But to do that, I have to get a common denominator, right? You can't add or subtract fractions without having a common denominator. And the easiest way to get a common denominator for this bad boy would be to take this term and multiply that term by the denominator of this term over itself. In other words, I'll take this and it'll become KQ x minus d over 2 squared over x plus d over 2 squared times x minus d over 2 squared. This guy over here, I'll do the same trick, except I'll multiply this by that denominator. So I've got minus KQ x plus d over 2 squared. I'm running out of paper, that sucks. Over x plus d over 2 squared, x minus d over 2 squared. That was a mouthful. But now that I have them all under the same denominator, I can rewrite it. Also helpful that I can rewrite it in a place where I've got more space. So as one big fraction, I've got K, Q, all over all right. And if I were you and I were seeing this expression, I'd probably be thinking, hey, I thought the goal was to make it prettier, and good God, that looks more complicated. And it kind of does. But let's simplify it down some more and let's see what happens. So what I'm going to have to do is I'm going to have to FOIL out these two expressions here because I want to collect some like terms in these places up top. So what's going to happen is this is going to turn into KQ times. Now, when I FOIL that out, I'm going to get x squared plus 2 this times this. So it's going to be, actually, minus x times d plus d squared over 4. Right? Do you see how I got that? I just did the FOIL method where it's first, outside, inside, last. So I imagine I'm multiplying this times itself. So I'm going to have x times the first term, then x times the middle term, and then this term times itself. Over here, I'll do the same trick. Minus KQ, I'll get x squared plus xd plus d squared over 4. All of it over all that disgusting, ugly stuff. This still looks pretty nasty, except now I can start to collect like terms. Because look what's going to happen. When I multiply KQ through, I'm going to have KQ times x squared from this, right? But over here, I'm going to have minus KQ times x squared. And what that means is that this x squared term and that x squared term, they're going to cancel. That's better. Now, I'm going to have KQ times negative XD. Okay, so it's negative KQXD. But over here, I'm going to have negative KQ times XD. So what's going to happen is this term here and this term here, they're not going to cancel. There's two of them. I'm going to have two of them. So I have minus 2 KQXD. Now I'm going to have KQ times positive D squared over 4. But over here, I'm going to have minus KQ times D squared over 4. That means that this term and this term are going to cancel. So that got way easier once I FOILed it out and combined like terms. Not really so bad at all once I do it this way. So here I've got my total electric field given by this. But we're going to go one more step further. Because what's going to happen is in a dipole, we usually have the distance x, the distance from the center of the dipole, is usually way, way bigger than the distance from one charge to the other. So what's going to happen is when I have x plus d over 2, I've got usually a really big number plus a super tiny number. And we're going to make an approximation, right? If I make the approximation that x is much, much larger than d, then that allows me to make the supposition that x plus a super tiny difference is still approximately the same as x, right? If I have a million zillion plus 1, it's still basically a million zillion, right? The same thing goes for x minus d over 2. A million zillion minus 1 is still basically a million zillion. So if I'm making the approximation that x is way, way bigger than d, I can get away with replacing x plus d over 2 and x minus d over 2, both of those with x. But if I do that, I'm going to have negative 2kqxd over, and now here I have x, this is x squared, times x squared, that's x to the 4th. And this x and one of those x will cancel. So after all is said and done, my final answer along that axis for a dipole is this expression right here. Now, obviously, in your background section, you're going to have to derive these expressions and explain to the reader why these expressions work. So hopefully you were paying attention during all of this. But notice it says that the electric field for this dipole ought to depend on Q. If Q gets bigger, I ought to get a bigger electric field. Today, we're going to prove that that's true. It also says that as D gets bigger, as the two charges get further apart, the electric field should get bigger. You're going to prove that that's true. It also tells you that if you take a dipole and you look at the field at increasing distances away from the center, as x gets larger, the electric field should get smaller. But notice this goes as x cubed. And we do this sort of functional reasoning in my class all the time, right? A regular point charge would have that distance on the bottom in the denominator, but it would be squared. But this is cubed. So if you had something that was squared in the bottom and you double the bottom, then the answer you get would go down not by a factor of 2, but by a factor of 4, right? But here for a dipole, if you double the distance away from the dipole, this says that your electric field should drop not by a factor of 2, not by a factor of 4, but by a factor of 2 to the 3rd power, which is 8. So the electric field ought to die off considerably more quickly for this dipole than it would for a simple point charge by itself. And you're going to prove that as well. But this is just the electric field along one axis. What about if I looked at the electric field along a different axis? Well, there it's going to look a little bit different. So let's try it that way instead. Same problem, different geometry. So this time what's going to happen is here's the axis of the dipole, and this is what we call a perpendicular bisector. I don't know why I made this one dotted, the other one didn't, but whatever. And what's going to happen is we're going to look at the electric field at a spot along this y-axis. Now, if I do that, the problem is a bit more complicated because this guy's electric field is not straight to the right, it's up and to the right. This guy's electric field is not straight to the left, it's actually down and to the right. And so what I'd have to do is add both of these electric fields together. And of course, when you add vectors together that are not collinear, you have to break them into components. So I'd have to split E plus and E minus into components. So first, let's find the magnitude of those. So to find the magnitude of E plus, that's going to be KQ over R squared. But I need to find the expression for R. And R for E plus is going to be that distance right there, which is not X anymore. Instead, this distance here, I'll call that Y. That's how high I am above the origin. And of course, this distance right here is D over 2. So this distance I would get from the Pythagorean theorem. And so I'd have KQ over, and since the Pythagorean theorem says that that distance should be the square root of y squared plus D over 2 squared, and this is R squared, all that's going to happen is I would square away that radical, and I'd have y squared plus D squared over 4. I got to square that whole thing. So that's the magnitude of E plus. From symmetry, however, the magnitude for E minus is going to be exactly the same thing. So yay, I've already done them both. So this is equal also to the magnitude of E minus. They're both the same. Unfortunately, I've now got to break them into components. And what's going to happen is this guy over here is going to make some kind of angle with the horizontal. And I know that I'm going to take this expression times the cosine. That's going to get me the x component. This expression times the sine is going to give me the y component. We've done that sort of stuff before, so hopefully that's obvious. So if I take E plus and I break it into component form, that's going to be KQ over y squared plus D squared over 4 cosine of whatever theta is in the I hat direction, and plus KQ y squared plus D over 2 squared sine theta in the j hat direction. Again, I hope this is pretty straightforward. The good news is for E minus, it's going to make the exact same angle, and the only difference is that E minus points downward in the y direction. So it's going to be this same expression, except that's going to have a minus sign. Awesome. Now, I want to find the total electric field, so I have to add these two vectors together. But when you add vectors together, what's going to happen is you add the x components to the x components and the y components to the y components. And what's really cool here is that the y components are equal but opposite. They're going to cancel. Don't care about those. The x components look exactly the same. So it's just that same thing doubled. So my total electric field is going to be purely in the x direction. And it's going to be KQ over yada, 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 times 2. Oh, but wait. This cosine theta thing's a pain because as I move higher and higher and higher in the y-axis, or lower and lower and lower in the y-axis, that angle is going to change. The higher I go, the steeper that angle is going to be. So that cosine of theta itself is going to be a function of y. So let's make that simpler. Let's see if we can't figure out how theta is an expression of y. And the way I can do that is by noting that this angle right here should be the same as that angle right there. And that's cool because if I'm looking for the cosine of theta, cosine is adjacent over hypotenuse, right? Well, the adjacent side of this little triangle is d over 2. The hypotenuse of this little triangle is r. So I can replace the cosine of theta with the expression d over 2 over the square root of y squared plus d squared over 4. So if I take this expression for the cosine and I plug that in here, what do I get? So now I've got E equals 2kq over y squared plus d squared over 4 times the cosine of theta, which is d over 2, all over the square root of y squared plus d squared over 4. Oh, that's really ugly. Let's simplify the heck out of that. This 2 and that 1/2 cancel. That's cool. And then here I have something multiplied by that same something, but square rooted. That's the same as taking that to the 3/2 power. So I've got k times q times d all over y squared plus d squared over 4 raised to the 3/2 power. So that's a little bit better. Except, again, we're going to make the assumption that my distance from the axis, y, is way, way bigger than d. So if y is much, much larger than d, I can approximate that y squared plus d over 2 squared, or there we go, d over 4, d squared over 4, is approximately equal to y squared. Because I'm taking a huge number, squaring that huge number, plus a tiny number squared is still basically the huge number squared. This is so small compared to this that I can basically neglect it. But now I have y squared to the 3/2 power. That's y cubed. Sorry, I was concerned that I'd made a mistake, but I did not. And by golly, that's pretty doggone simple. And you'll notice this expression that we got along the perpendicular axis looks remarkably similar to the expression that we got along the other axis. Look, it's kqd for both of them in the numerator, the distance from the axis cubed in the denominator, and all that's different is that I've got this factor of 2 up here. The minus sign's about the direction. I don't care so much about the minus sign. It just points out the obvious, that if I'm looking at the electric field here, it points to the right. That's why it was positive for the y part. But if I'm looking for the electric field over here, I'm closer to the negative charge than I am to the positive charge. And as a consequence, it's going to point to the left. So we don't really care about the direction so much. We're looking more at the magnitude. So these are the two expressions that you're going to compare your experimental results to, right? That's where that comparison is going to come from. You want to see how well this holds up. And notice you're going to have to test all 3 dependencies. You're going to have to prove to me that it's going to be linearly increasing with q, linearly increasing with d, cubically decreasing with x, and cubically decreasing with y. And so that's what we're going to do. That's the experiment that we're going to test. We're going to look to see if these results pan out. All right, so that was me talking for a really long time and none of you guys made any noise. Any questions about that? I'm going to take your silence for a no, this is perfectly sensible, and we're all going to get A's, and not just a admission that your microphones aren't working. Thank you, Max. Shut up. So, to pull this off, you're going to end up going to this simulation for charges and fields. We're going to use this as our little experimental tableau. And you've got a number of tools available for you to use, right? You can place point charges in places, right? And you can build a dipole. Now, I find that putting the electric field lines here is kind of distracting, so I tend to turn that off. This grid often helps me determine at a glance whether I'm lined up properly. So what I would do is build a dipole, and you've got a total of 6 objectives, right? And what's going to happen is I'm going to take this dipole for reasons that should become obvious in a minute, and I'm going to put it way down here out of the way. And you'll notice I'm starting out with my 2 charges basically as close together as I can get them. And I'm trying to keep them centered on one of these little grid lines so I can tell that they're lined up properly. And what's going to happen is if I turn on the value setting, I can place a sensor in different places, and you can see that as I move that sensor around, it's telling me 3 things, right? It's showing me an arrow for the direction of the electric field that's scaled. It's telling me the magnitude of the electric field. That's the 32.8 volts per meter. That tells me how big the electric field is at that location. And it's also got the angle that the field makes with the horizontal. Now, I'm looking at the electric field along this axis or along this axis. So what I would do is I would place this sensor somewhere along that axis, and you can see that if I get it on the axis just right, the electric field should be completely to the left, and right now it's a negative 179 degrees. It would be 180 if it was perfect, but it probably won't get perfect. But at that location, I've got an electric field of 46.2 volts per meter. Now, if I move my sensor further away, the electric field gets wimpier. Again, that's what we were just seeing. We expect that as we get further from the dipole, the electric field ought to get smaller. And I want to prove that the relationship that I see is going to end up being the one that we just derived. So how can I pull that off? Well, I could put in a bunch of sensors. So there's one sensor. And I'm going to start with some of the sensors pretty doggone close. And I'm going to keep going until I get pretty doggone far away. I want to have a pretty good range of data. And I'm trying to keep them all along that same axis. So notice this angle is trying to be as close to 180 as I can get it. And so now I've got a bunch of data points. At this point, that's so tiny, going out much further, I'm not going to be able to read much. But there's my expression, right? And I can take each of those with data points, and I can measure how far they are from the center of that dipole. Here's my little tape measure. I'm going to put this little plus right here in the middle. And I can see that that first sensor is 50.4 centimeters away. The next one is 100 centimeters away, 151, et cetera, et cetera. So what I can do is I can measure the different values of X and the different values of E, and I can plot those. Now, if I plot those things, what do I expect to see? You don't know, Tom, because we're not responding to you. So if I were to plot a graph of the value of x, that's the distance from the center, versus the value of e, what I expect to see from theory is a cubic, an inverse cube, because the formula that we're trying to verify was that, right? That's the thing we got when we just derived it. Now, you're not plugging numbers into this formula. Don't do that. Instead, what you're going to do is you're going to plot this graph, find a trend line of that graph, and then verify that the trend line matches this. One thing that you could probably do, because we do this a lot, is that, you know, weird curvy lines like this all look the same. However, if you instead plot it in a clever way, if you plot e as a function of not x, but 1 over x cubed, then what you should find is that you will get a straight line. If the theory is correct, that plot ought to be straight. And so essentially what I'm doing is taking 2kqd. I basically separated this out to be my x variable. I pulled this out to be my y variable. That implies that my slope ought to be that. So for objective 1, that's what you're going to end up doing. What about objective 2? Well, heck, I don't even have to move my stuff. Objective 2 is to do that same expression, or that same experiment, but this time, do it along the opposite angle. Again, I'm trying to get this thing to be as horizontal as I can make it. That's probably about as close as I'm going to get. And so again, I have sensors placed at varying distances along that axis. So for objective 2, I expect to get a similar expression, right? The theoretical expression that I'm expecting to see for objective 2 is that E ought to equal KQD over Y cubed. And again, what are we varying? We're not changing D, we're not changing Q, we're only changing Y. We have several different values of Y. And I expect that if I plotted that graph, I would again get some annoying parabola. But if I'm clever, I don't plot E versus Y. I instead plot E versus Y cubed. That's going to give me a straight line, and the slope of that straight line will be KQD. So you can verify that. That's your objective 2. Now we also have to test the other parameters. You have to test whether or not the dependence on the charge or on the distance between the charges pans out the way you expect. How am I going to pull that off? Well, for that, I don't want to have measurements at a bunch of different distances. I only want to have measurements at one distance. And what's going to happen is I want to be able to test this, but we made an approximation in those derivations where we assumed that the two charges were separated by a distance that was way, way smaller than either X or Y. So what's going to happen is I don't want to have sensors that are super, super close. So maybe I pull those sensors off for the last couple of objectives. And I leave some sensors that are pretty far away. That's why I put the two charges in the bottom corner like this, was so that I had plenty of room to get further away. Now, what's going to happen is, right now, how far apart are my things? What is D? Well, according to my tape measure, if I put this one in the middle of the positive, right now I'm pretty close to 20 centimeters for those two separations. And what's going to happen is, I don't want to change how far my sensors are from the center point of those two things, but I want to make them, the two charges get further and further apart. So what I'm going to have to do is move them further apart, but keep the center of them in the same place. So what I might do is move this guy one little tiny box to the left, or to the right, excuse me. I'll move this guy one box to the right. So the center is still right here. And that means that the distance from this to the center hasn't changed. But you'll notice my electric field is a little bit bigger than we saw previously. And so what I can do is take data points there, keep making this separation bigger, measure how big the electric field is. Notice I can do both objectives 3 and 4 at the same time. And again, I'll do a plot. And what does the theory suggest? The theory suggests, doggone it, I didn't mean to do that. The theory suggests that if I plot the electric field as a function of D, then I ought to get a straight line. What should the slope of that straight line be? I'll let you figure that out. Then I'll go back and I'll do the same thing, except instead of having my charges get further apart, I'll put them back at their original super tiny distance. But this time I'll change the charge. Right now I have one of each, so it's 1 nanocoulomb in either case. Here I'll take another 1 nanocoulomb and put it on top of it. Now I have 2 nanocoulombs. And again, what we expect to see happen is, if I plot E versus Q, I expect again to get a straight line. The slopes should be different for this point versus this point, and you're going to determine whether those comport to the theoretical values. So that is the goal that is laid out before you. Hopefully you guys know what's going on. Normally I would break you guys up into groups and have you guys work together on stuff, but there's only one set of you, so talk amongst yourselves. Or you can sign off and do this solo, I don't care. But if you have questions, feel free to ask me.
Can you actually assist me with the coulombs? Excel, I think I did it wrong. I'm not sure if